Hello guys, welcome to Self-Help Maths Academy. We'll continue with the examples. Here in this example, we're showing that every bounded function need not to be R integrable. So we know that every integrable function is bounded. So we are showing now that every bounded function need not to be R integrable. Okay, with the help of example. So let us start with the example. Consider a function f defined on the closed interval say 0 to 1 by f of x equal to say 0 when x is rational, when x is rational, and it is equal to 1 when x is irrational, when x is irrational. Okay, so we are defining our function like this. So clearly our function f is bounded because we are defining it in the closed interval 1. Our f of x is between 0 to 1. Clearly f of x is bounded. It is bounded since because your f of x lies between 0 and 1. This is true for every x belongs to 0 to 1, closed interval 0 to 1. Now we will take the partition, say if p is equal to 0, which is x naught, say x1, x2 and xn, which is equal to say 1, is any partition. It is any partition, okay, of the closed interval say 0, 1. Then I will take any say the interval, subinterval, for any subinterval, for any subinterval say IR, this is equal to xr minus 1 xr, where r is equal to 1, 2 and n. We have what is our capital MR is, since our function f of x is 0 if x is rational and it is 1 if x is irrational. So capital MR is equal to, here in this case our capital MR is 1 and small mr is 0. Okay, so therefore upper dot box sum is equal to summation of capital MR delta R, where R is running from 1 to n. So the capital MR is 1 and delta R, simply it is xr minus 1, xr minus xr minus 1. So we'll write this as xr minus xr minus 1, where R is running from 1 to n. So this is simply what? If I put n, this is xn minus x naught. Okay. So this is equal to, because the interval, this is nothing but, we know that the interval we divided in between them, that is equal to, this is our, let us take this as 1. Okay. Xn minus x naught is equal to 1. So and our, since it is 1 minus 0 which is equal to 1, here lower dot box sum, this is equal to summation mr delta r, where r is running from 1 to n. This is equal to 0 into xr minus 1. 0 into anything is 0, so it is 0 here. Okay, so therefore let us take the lower integral f of x dx. This is equal to supremum of the lower dot box sum over the partition 0 to 1. This is equal to, since the lower dot box sum is 0, so it is 0 here. Now again, this is 0 to 1 f of x dx. This is infimum of the upper dot box sum, where over the partition p from 0 to 1. So this is again, upper partition is 1, so this is equal to 1 here. Okay, so here if you observe, the lower Riemann integral is not equal to the upper Riemann integral. So therefore 0 to 1 f of x dx is not equal to 0 to 1 f of x dx. The lower Riemann integral is not equal to the upper Riemann integral, and f does not belongs to the, f is not the therefore it is not R integral, Riemann integrable. F is not a Riemann integrable function over the closed interval 0 comma 1. So this is one such example where we are trying to show that the given function is bounded but it is not R integrable. Okay, so now let us see another example. Let us see another example where show that you have f of x equal to 2x plus 1 is integrable on the closed interval 1 to 2, and integration from 1 to 2 f of x here is 2x plus 1. Let me write that. 2x plus 1, this is equal to 4. Okay, into dx equal to 4. Let us prove this one. So to show that, consider the partition. Consider the partition. Say P within the interval 1 to 2. I'll take that as 1. Say 1 plus 1 over n, 1 plus 2 over n, and so on. Say 1 plus n over n. So this will be 2 and this is 1. Okay. Dividing the interval 1 to 2 into n equal parts. Okay. Now let us take for any subinterval. Then for any subinterval, we consider for any subinterval, say IR, which is equal to 1 plus R minus 1 by n. Okay, 1 plus R by n. So let us take this as one of our subinterval, R equal to 1 to n. If I put n equal to 1, I'll get 1 here. If I put n equal to 2, I'll get 1 plus 1 by n, and so on like that. We'll be getting all the required partitions, okay, by substituting the R values. So here our capital MR is equal to, since our function is 2x plus 1, so it is 2. Here x will be here. In this case, for capital MR, we take this one. For small mr, we are taking this one. Okay, so let us take this one. Now 2 into x, that is 1 plus r by n plus 1. This is equal to 2 plus 1, that is 3 plus r by n. This is your 2r by n. Okay, so this is your capital MR, and for small mr 2, this is your x, right? This is 1 plus r minus 1 by n plus 1, which is equal to 2 plus 1, that is 3. 3 you will be getting here 3 plus 2 into r minus 1 by n. So this is our small mr. And what is our delta r? Delta r is this minus this. So this will be simply, we will get 1 by n. Okay, that is the, since our function, you can write the reason, since f of x is equal to 2x plus 1, it is increasing in the closed interval 1 to 2. So therefore we have taken these values. Now the lower Dow box sum is equal to summation small mr delta r is running from 1 to n. This is equal to summation, what is our small mr? That is 3 plus 2 into r minus 1 upon n. R is running from 1 to n. Okay. Now this is equal to, if I take the LCM here, so this will be what? You can just write this. Let me write this one as 3n plus 2 into r minus 1 upon, say, n. If I take all the the terms which are other than r, I'll take out. So it is simply 3 into n upon n plus 2 by n, okay, into summation of r is running from 1 to n, r minus 1. So this is how we get. Okay, this is what we are getting here. Okay, so this one will be now into, yeah, sorry, I'm sorry, this one is This is our MR, and how about delta R, which is 1 by n, right? So 1 by n. This will be now n square. Yeah, this one will be n square. Okay, all right. So this is the value. Now what we're getting, this is equal to, we write this as 3 plus 2 by n square. So summation of r minus 1 is simply like n, in place of n we have what, r minus 1. So this one we can write it as n minus 1 into n upon 2. Okay, yeah. So this 2 cancels. So 1 n also we can cancel. So here we're left with 3 plus n minus 1 upon n. Okay, so or we can also write it as 4n minus 1 upon n, or simply 4 minus 1 by n. Okay, so this is your lower Daubox sum. Okay, now let us write the upper Daubox sum. This is equal to summation capital MR delta R. When you're doing, you have to be very careful with the signs. So this is equal to summation 3 plus 2R upon n. This is our capital MR, and delta R is 1 by n, where R is running from 1 to n. Okay, so now in this case we get summation of, okay, so let me take everything in that if n is the LCM, it is simply 3n plus 2r upon n into 1 by n. Okay, so this will be simply what, here we take this, if I take n out, so it is which are the free from I mean, like, the terms, we will take here 3n by n. Okay, yeah, then this one will be 2 by n, this n and this n, it will be n square plus 2 by n square summation of r. R is running from 1 to n. Okay, so this is equal to, here we get 3 plus 2 by n square. This we can write as n into n plus 1 upon 2. So 2 cancels. 1 n also we can cancel. This is equal to 3 plus n plus 1 upon n. Okay, so this is equal to 3n plus n, 4n plus 1 upon n, or we can write as 4 plus 1 by n. Okay, so this is your upper Daubox sum. Okay, now we have got the lower and upper Daubox sum. Let us consider the lower and upper integral. So 1 to 2 f of x dx, this is equal to supremum of the lower Daubox sum for over the partition P from 1 to 2. Okay, this is equal to limit as n tends to infinity. So this is the lower Daubox sum is 4 minus 1 by n. As n tends to infinity, this tends to 0. So here we are left with what? It is equal to 4. And for the upper Daubox sum, say 1 to 2 f of x dx, this is equal to infimum of the upper Daubox sum, where it belongs to 1 to 2. This is equal to, here we have limit as n tends to infinity. This is again 4 plus 1 over n. This as n tends to infinity, which is equal to again 4. So clearly both are equal. So since our upper Daubox sum and the lower Daubox sum are equal, this is equal to 1 to 2 f of x dx, this is equal to 4. Hence our function is integrable and the value is equal to 4. So f is r integrable over the closed interval 1 2, and integration from 1 to 2 f of x dx is equal to 4. Okay, so this is how we have to prove the given integral. Now I think I'll give you one for yourself to practice. So you have to prove that integration from 1 to 2 f of x dx is equal to 7, where your f of x is given by 2x plus 4. Okay, maybe you can take the closed interval where x belongs to the closed interval 1 to 2. Okay, just prove this is equal to 7. All right, and put the answers in the comment whether you're getting it, and what is your upper double sum, what is your lower double sum, that we will discuss. Okay, I think that's all in this video, and then we will solve I think some more examples and properties in the next video, and we'll come up with the next concept. Okay, till then, take care guys.